on chapter 7 in your chemistry book, and we're talking about light, electrons, and atomic structure. We went over all of that, but the last part was of your chapter here is a little section on the frontiers of chemistry, and it talks about chemical lasers and energy. How did lasers come into being? It was all of our study that we've done on the midst of when we're talking about quantum mechanics that led us into being able to discover about lasers. And so this is a frontier, and it's still ongoing frontiers, you'll see and know. But anyway, how did this start? Well, electrons in excited states, they drop back to these lower energy levels, and then they emit photons, and that's how we get light, right? In a fraction of a second. Well, Albert Einstein in 1917, he said if an atom is struck by a photon and of the correct frequency during a brief excited state, something different happens. Instead of emitting just one photon, that atom will emit two photons that are identical to each other. And then it will return to ground. And here's kind of a picture. Here we have the electron coming in. As the electron comes into the excited state, in the excited state of the atom. And here's the photon strikes, still excited, this atom. And then all of a sudden the atom would emit two photons, which will give a very bright light. So, well, it wasn't until like 40 years later that a man named, what was his name? Let's see here now. Theodore Maiman. Let's go on to the next page and I'll tell more about it. Theodore Maiman, who lived in 1927 to 2007, and he harnessed the stimulated emission. That's what basically Einstein called it, was stimulated emission, to produce narrow beams of high intensity light. And Maiman named this high intensity light laser. And since 1960s, lasers had found a tremendous variety of uses. We use them in DVD players, we use them in all different things, like, for eye surgery, and to cut through diamonds, and to cut through titanium, and all these lasers are so important in the world that we live. Here's a picture of a ship-mounted laser test system. So how amazing is that? So basically, these lasers he found were extremely intense. In fact, 5 times brighter than the sun. And you can imagine. And a 130-watt infrared beam of laser could slice through sheet metal and titanium, which is titanium, I should say, which is very, very hard to do. So anyway, and coming down here, it talks, you can read the rest of this, but it talks about lasers, and it'll talk about this laser here that has to do with the argon fluoride excimer laser, which actually it is the excited stage of those argons and fluoride, and it turns and as it bumps off argons 3p electrons up to the 4s level, and they become very excited, and they produce this high laser, and they use this laser for correction surgery of people's eyes. So you can imagine, have you heard of someone having laser surgery on their eye? That is this. I mean, if we didn't know about photons and stuff, we wouldn't know about lasers, would we? In fact, this here describes coil, and what coil is the oxygen iodine laser, and it burns hydrogen peroxide and chlorine to produce excited oxygen, which then reacts with injected iodine gas to form excited iodine. And it goes through this whole equation here. And these coil systems have been used and tested for missile defense. So lasers are used for a variety of subjects now, and coming from the study of light and quantum, the quantum theory and quantum numbers, and all that we're studying has to do with the future and what's going on now. So I'm gonna go over some of these questions really quickly because some of these might be on your test. So let me find my section review. Oh, here we go, section review. So name each of the four quantum numbers and tell what property of orbitals each one. Remember those four quantum numbers? I'll put it here so you can see better. Four quantum numbers. Remember we have the N, L, M, and MS. So here is, see if you can see this, I don't know. So you have N being that energy level, L being the shape of the orbit, M being the orientation in space, and MS being the spin. Just remember 1, 2, 3, 4 quantum numbers, okay? So what is the shape of each of the following orbitals? 2s, S has a sphere shape. 4p would be, basically that P would be a dumbbell shape, but had be 4 of them, you know, so it would look kind of like a cross dumbbell, right? And then 6s would be 6 spheres. So those are the following orbitals in the that are in the shapes of those orbitals in the L level, which is the subshells. So state the Pauli exertion principle. How does the principle limit the number of electrons in each orbital? Pauli exclusion principle means that, or states that no 2 electrons in any atom may have all 4. Remember these four different things I suggested, may have all 4 of these quantum numbers. So no 2 electrons in one atom may have all 4 of these same quantum numbers. So that's the exclusion. It's exclusion, saying you can't have all 4 of those numbers the same for 2 different electrons. How does this principle in an atom? How does this principle limit the number of electrons in the same orbital? But basically, those in the same orbital are not going to be identical. So usually you have a spin. One's going to spin counterclockwise and one's going to spin the opposite, clockwise. So how does Hund's rule affect the order in which orbitals are filled? Remember Hund's rule? Hund's rule says that one electron, there has to be one electron occupying the orbital in that substance before pairing begins. Basically, it says if you have an electron, the single electrons are going to be used in that space before the pairing of electrons happens. Just pairing doesn't happen until all of the single electrons are used. What are valence electrons? Valence electrons actually are those, usually when you say valence, it has a positive or negative charge, but valence electrons are actually those electrons that are involved in chemical reactions that move in such a way in an orbital of another atom to put molecules together. So they're involved in chemical reactions. The Lewis symbol, I hope you got the Lewis symbol. Let's go back to those symbols there. The Lewis symbol would just say, why are Lewis symbols useful? Because they tell the valence of things and tell how a certain type of element's going to react. Let's go back to that and I'll show you. Right here, Lewis numbers, these are the Lewis, and they're used on the periodic table. It has atomic number here, the Lewis numbers here, the electron configuration. 2 would be in the first shell, 8 in the next shell, and then 4, but this shell's not filled yet, so you have a valence electrons of 4. And so these electrons are going to be, how are they going to be put? Well, we put 1, 2, 3, like this, 1, 2, 3. And then basically after 3, we go put 1 here, and 1 here, and 1 here, and then we go back and fill them in. So that's your Lewis number, but it's telling how these, like all of these will have the same number as valence, and which ones have the same number. Like you'll see these are all full number with 8s at the end, and they all kind of, and you go to the periodic table and all of these that are elements in these columns will act the same. Like here's, hydrogen and lithium and sodium having just 1 valence, and they all kind of act the same. So that's pretty important. Let's go back to our questions. I don't know if I'll get through all of our questions today, but so what is the maximum number of electrons that can occupy, the following? So remember that formula? Let's see what that formula is. Basically, go down here and see if you have the formula in the review. Why am I? Oh, I guess the formula's not there. I wanted to show you that formula, so it's very, let's see, where do we? The formula actually is, let's go back to it. It's important to look at it. Not for me just telling you what it is, but to look back at it. Mm-hmm. Oh, sorry, I don't see that formula right away. Let's go back to the question. Basically, the formula is going to be that n times n, 2 times n squared. Remember that formula, 2 times n squared? So that's going to be our number. So that we find how many are in that. Here in my notes, I can tell you in my notes. It's 2n squared. So 2 times n squared. That's the number. And that will tell the maximum amount of electrons, 2 times n squared. Mm-hmm. So you have basically one shell. You say 1 square is 1 times 2 would be 2. So this would be 2. This is 3, so it'd be 3 square, which is 9, times 2 would be 18. So basically 2n squared. Give the number and types of subshells that are possible for each of the following. So let's look at each of those following ones. Let's see. So in this first one, n is 2. So there's actually a table to look. That's what I was kind of looking for too. There's a table back here that tells. In fact, we should go back to that table. Give the number of types of subshell find for this one. So let's go back to that table again. Sorry, I'm losing this. There's a table here that you can find. I think it's, not there yet. Here it is right here. The relationships of n and the number and type of orbitals. So for one n, you're going to have one s. So what does it say here? What was our question here? So one n would be one shell and one orbital, one s. So, and on to 2, I think 2 is the next one. Actually, A is n equals 2. N equals 2, you'll have one s orbital and 3 p orbitals. It goes by like kind of odd numbers. The s are 1, 3, 1, 3, 5, 1, 3, 5, 7. So it's an easy way to remember. And so now on to, if you have 3 is going to have one s orbital, 3 p orbitals, and 5 d orbitals. So that would be for 3. What was the other question? N equals 4. N equals 4 is going to be 1s, 1p, 1d, or 1s, 3p, 5d, and 7f orbitals. So that's the relationship. Just remember as it goes. 1 is s, and then s and p, then spd, then spd and f. So as the amount of orbitals. So let's go back. The questions. Okay, how many electrons maximum can a D subshell contain in an F subshell? So a D subshell we saw can contain, we just went over that, can contain 5, and an F can contain 7. So we just went over that whole thing. So write the Lewis symbols for the following elements. So let me put this on here so you can see this. You can see it pretty well. It's kind of like the light kind of reflects there, but Okay, I hope you can see this here. Well, here is the Lewis symbols, and here's how you put them around here. So the first one is for carbon. So if you go back to the periodic table here, you'll see carbon. Here's a C, and then you'll see 2 and 4. So now we know these 4 we have to put around. How are we going to put these 4? 1, 2, 3, and then 4 over here. We skipped here, this one. So 1, 2, 3, 4. This is carbon. Carbon has 6, atomic number of 6 and 6 electrons, 4 and 2. Here's hydrogen, very easy. There's hydrogen, the number 1 and 1. So you just put 1. Here's selenium. I hope you're seeing this okay on here too. Here's selenium. And so basically you have 2, 8, and 6. So you need to put these 6 valence. 1, 2, so you have 1, 2, 3, and then 4, 5, and then you go back and put 6 down here. Remember, you skip them, they skip one, and then go back and fill them in. Xeon. A little closer there. You can see that. Xeon is a XE. I don't know if you can see that there. So XE, and then you have 2, 8, 18, 18, and 8. These 8 have to go on, so 1, 2, 3, 4, 5, 6, 7, 8. They go all the way around it. So that's all you have for there. So write the Lewis symbols for an element having 7. So I looked in there just to find an element in the periodic table, and I found one here, and it's basically fluorine. And fluorine has 1, 2, 3, 4, 5, 6, 7. 7 dots. So that wouldn't be too hard. Okay, so let's go on to the chapter review. See if there's anything in the chapter review. I hope you know how to do those. Those are pretty fun actually to do. So the first question says, as a wave frequency increases, what happens to the wavelength? As the wave frequency increases, the wavelength go down. They're opposite. Number 2, of what type of wave does light consist of? So what type of wave is electromagnetic wave, electromagnetic light, right? The electromagnetic scale. Give the speed of light in a vacuum in meters per second to 3 significant figures. Be 3.0 times 10 to the 8th. So you have to change that to 3 significant figures, but actually be, you're going to be able to take 10 to the 8, and you're putting those 8 down. So anyway, basically it's 3.0 or 186,000 miles per second. What is the electromagnetic spectrum? Into what 7 broad categories is it commonly divided? So you can look that up there, but it's pretty easy. With the largest wavelength and the smallest frequency, you start with radio waves, then onto microwaves and infrared waves, and then you go to the visible waves, and then the higher frequency are ultraviolet, X-rays, and gamma rays. Okay, so into what 7 broad categories is commonly divided into the electromagnetic spectrum there, right? Okay, let's go on to number 5. State the quantum theory of light. The quantum theory of light is that electrons are packed in quantums, or are packed in these little packets of energy, right? Number 6, what is a photon? Is that packet of energy, that it's packed in. Distinguish between a continuous spectrum and a line spectrum. Well, the continuous spectrum is like a rainbow with all colors coming together, right? Through it, but you put light through a crystal like. A line spectrum is some element is heated at high temperatures and only certain colors appear in this line spectrum. So we had that. What is the primary difference between the Bohr model of the atom and its predecessor, the Rutherford model? Well, the Rutherford model talked about planets going around, kind of like little electrons were like planets going around a nucleus. So electrons look like that. Well, the Bohr said these electrons, they're in little packets or quantums, energy levels. They're not just a lone electron going around. They have energy levels, and they're in these packets of quantums. So, okay, define ground state. Ground state is the lowest state the electron falls to, right? Is that lowest state. State the uncertainty principle in your own words. Uncertainty principle means that basically we cannot be sure of certain electrons' position and their momentum together. They never are the same. The position and the momentum never, if you calculate one, the other one will be wrong. So it's very uncertain when it comes to electrons in that area. Distinguish between an orbital in the electron cloud model and the orbital in the Bohr cloud. Well, the electron cloud is the probability of that electron being in that place at a certain time. And the Bohr basically just says that they have little energy levels, but doesn't talk about the probability of where the electrons are going to be. What 4 qualities of an electron do the 4 quantum numbers describe? I think we went into that, those 4 numbers. They describe the characteristics of the energy level, the shape, the orientation, and the spin. Remember that? So number 13, what is a quantum number? Quantum number describes these characteristics, of it. So, and then state the Pauli exclusion principle. It says no 2 electrons may have the same 4 quantum numbers. They can't. It's no 2 electrons of the same atom will have the same 4 quantum numbers. So that's important. Number 15, what are valence electrons? What is the maximum number of valence electron the atom can have? The maximum number is 8 of that valence in that. So when you're doing those dots, 1, 2, 3, 4, 5, 6, 7, 8, that would be a full. So valence electrons are those electrons used to chemically combine with others and make them, they'll be able to combine with more electrons or lose electrons, gaining electrons or losing electrons. So the active ingredient in a particular sunscreen lotion absorbs light waves of 265 nanometers, most efficiently. And what region of the spectrum is this wavelength? If you looked in this section, it's in ultraviolet light. Look back to that chart, it tells what the wavelengths are. And if you look on it, of course, you think it would be ultraviolet light. Isn't it UV light? It's what we want to be afraid to get a sunburn with. Ultraviolet light can burn us, give us a sunburn. So microwave ovens use microwave radiation to cook food. Are microwaves longer or shorter than X-ray? Look back to that electromagnetic spectrum and you'll find that microwaves are longer than X-rays. X-rays are very frequent and very short, very, very frequent and short, and microwaves are long. Give the Lewis symbol of nitrogen. Well, let's see if you can see this here. Right here, nitrogen here. So nitrogen has basically 7 electrons, 2 in the first, and the next in the 5, there's always 2 in that first one. And so then you have 5 of them here. So you put basically nitrogen and you put 1, 2, 3, and then you put 4, 5. Now if you have 6, you'd go back and fill in. But so you go 1, 2, 3, 4, 5. That's nitrogen. Okay, let's see. How many valence electrons are there in each of the following atoms? So we look at each of the following atoms, we look it up at the valences, you'll find, and you'll see hydrogen has 1. You can look them up in the periodic table. In fact, let's go back to that right quick and we'll show you. Right here. So the first one was hydrogen. Hydrogen here has 1 valence. See the little dot? And iron, which we know what iron is, right? Iron is Fe. You can find basically Fe on here. It's down further, I think. Let's see. Iron has 7. So that's fluorine. I'm trying to think of iron on here. I should know exactly where it is, but iron has 7. My mind is kind of going blank here. But iron has 7. Beryllium has 2. Chlorine has 7. Chlorine has 7. And aluminum has 3. Neon has 8. But you can get them all from here. So beryllium's here, that's 2. So just looking at some of this. Neon, here's neon having 8. Aluminum here having, what did I say? Aluminum having 3. So you just have to look these up on here. Let's see, what else did I see? Neon is 8. I think I said that. Okay, just look these up on here and you'll find out. This counting these little dots, we'll find out where everything, you know, where they are in the midst of all of these. As you go down and looking through all of these, you'll find out which one, and you'll see the dots of them. So, okay, let's go back. I think that's all I'm going to go over. Although there was one more section, one more thing that was pretty interesting. Write the Lewis-Silden symbol. Oh, what are the valence electrons? We did that. Okay, down here at the bottom. Give the Lewis symbols for the following. So I did those here. So basically you put a Z, and then you'll have 32, where you're going to have 2 in the first. So here's Z right here, this kind of one with 32. So you'll have 2, 8, 8, 8, 6, kind of like 2 or whatever, but you end up putting, you'll have 6 in the last, so you 1, 2, 3, 4, 5, 6. So you put the valence. Then you'll have Z equals 18. Here's 18 down here. Here's the Z. And so you'll have 2, 8, 8. I always put 8, 8. And they'll have 8 in the last. So 1, 2, 3, 4, 5, 6, 7, 8. So that's the answer for that one. 5, basically 5 valence. You'll have, let's see, 5, you'll have 2, and then you'll have 3 left over. So, and 1, 2, 3. 19, you'll have 19, you'll have 2 in the first, then you go by 8. Where do I have, what number is that? Let's see. That's D right here. 19 would be 2, 8, 8, and then you have 1 left. So you have Z with just 1. You just go by 2s and 8s is what you're going to do in the midst of when you're finding these out. So we'll have to probably tell you about that later, but that's all. We're done.